In this video, we present our work, RePOSE, Fast 60 Object Pose Refinement via Deep Texture Rendering. I am Shun Iwase, a second-year master's student at the Robotics Institute at Carnegie Mellon University. Fast and accurate 60 object pose refinement is crucial, especially for many robotic and AR applications. Therefore, our research question is that, how can we refine an initial 60 pose fast and accurately? Most recent works adopt a regression-based 60 object pose refinement methods. The architecture is simple. Given zoomed-in input and rendered images, CNN outputs a refined object pose iteratively. However, this approach has several drawbacks. First, the runtime of CNN for zoomed-in inputs is slow, which is especially prominent for multiple object pose refinement. Second, RGB texture is required for a compare and refine design to render an RGB image of a 3D model with an estimated pose. Third, since projective geometry is not considered explicitly, it requires more training data to learn the mapping of the deep feature into an object pose directly. To address these problems, we propose a novel 60 pose refinement method called RePOSE. Unlike the previous works, RePOSE iteratively refines an object pose by minimizing the feature-metric error between the input and rendered image features fimp and frend via Levenbach-Marquardt optimization. Texture parameters and the unit decoder are optimized during training such that an object pose is refined within few iterations. An element-wise error between the features is considered explicitly. RePOSE works well even without zooming in. Since the feature frend is computed simply by rendering a template 3D model with texture parameters, an RGB texture of the model is not needed anymore. We call this technique deep texture rendering. By bypassing CNN, it takes less than a millisecond for the feature extraction of frend. In addition, recent 60 object pose estimators also utilizes a unit architecture as well as RePOSE. Thus, the extracted features from the unit encoder are shared for further speeding up. As a result, RePOSE runs at 92 FPS for a single object with 5 iterations. All operations such as image rendering, Jacobian computation, and Levenbach-Marquardt optimization of RePOSE are fully differentiable. We train the network to minimize the mean distance between the vertices transformed by ground truth and estimated 60 poses. For evaluation, we test our method against the latest methods on the line MOD, occlusion line MOD, and the YCB video datasets. As shown in the table, our scores are comparable or better across all objects than the current art efficient pose. The average score is a bit lower, but the number of wins shows that RePOSE achieves better performance on more categories than efficient pose. This is the result on the occlusion line MOD dataset. Our method achieves the best accuracy at the time of publication. We additionally report AUC of ADDS scores on the YCB video dataset. Our method achieves the comparable performance with a faster runtime than previous methods like DeepIM and Koji pose. We confirm that the accuracy is improved decently even with only one iteration with much faster runtime. This is a qualitative result on the occlusion line MOD dataset. These examples show our method works well even with occluded objects. In conclusion, we presented RePOSE to improve the previous methods on 60 object pose refinement. We experimentally demonstrated the faster runtime and shorter or comparable performance of the proposed method. As future works, we will extend RePOSE for pose refinement of non-rigid objects. In addition, we plan to rewrite the code with JAX and CUDA for even more faster runtime. For more details, please refer to our webpage, GitHub repository, or our paper. Thank you for watching.